Oi de novo, gente. Vamos lá para a segunda página da Sincomp. Eu sou o João Guilherme, eu sou um homem cis branco de cabelo preto encaracolado. Meu background é uma parede branca com uma estante, uma parte do estante. Ok, agora nós vamos ter uma palestra do Pablo Samuel Castro. O Pablo, ele é um pesquisador da Google Brain de Montreal. E ele fala espanhol e inglês, então o que rolou foi que ele primeiro gravou a palestra e a gente aqui da Sincomp adicionou legendas. Nós vamos passar para vocês a palestra gravada com as legendas bonitinho. Quando terminar, ele vai entrar aqui para responder as perguntas, e aí vocês podem mandar em português, que a gente traduz, ou manda em inglês, que a gente repete, e ele vai respondê-las, eu creio que em inglês. Então, valeu, e acho que é isso.
Hello, everyone. My name is Pablo Samuel Castro, and I am going to be giving you a very brief introduction to reinforcement learning. I will very briefly go over my background. So I'm originally from Quito, Ecuador, and I moved to Montreal to do my undergraduate studies first, and then I continued on to do a master's and PhD, focusing on reinforcement learning. So I graduated at a time before AI was cool, like it is now. I did get a postdoc position, but I had a hard time finding an academic position, which is really what I wanted to be after PhD. But I was lucky enough to find a job in Google as a software engineer in ads. So I was still doing machine learning, but it was applied. So I wasn't doing research anymore. And this was a really great position. I learned a ton there. But this was in Pittsburgh. After 4 years, we decided to move back to Montreal. And there I was still doing more engineering work, back-end infrastructure for machine learning models. And then after a year of that, I was lucky enough to be asked to join the Brain team, which is where I am now. And so now I'm focusing on pure research, reinforcement learning research mostly, but also some research combining machine learning and creativity. And so today I'll be giving a little background on reinforcement learning and what this field is. So in a nutshell, this picture kind of captures what we're doing with reinforcement learning. So the main pieces in reinforcement learning are typically what we call the environment. So this is where you have an agent, and the agent is what you're trying to teach. You're designing algorithms so that the agent learns. And so the agent learns by sending actions or making decisions and sending these decisions to the environment. And the environment will return the next state, so where the agent ends up. So if you think of moving, if you say a robot says move forward, the environment might say, well, okay, now you're 10 steps ahead or 10 centimeters ahead or something like that. And it will also give it a reward or a cost. And this reward or cost is essentially a signal that says how good was that action that you just took. And the agent needs to incorporate this reward into its learning algorithm so that it learns to take decisions in order to maximize these rewards or minimize the cost. So this is somewhat different than what you typically think of when you think of machine learning or AI, where often the examples given are, classifying images or generating images or that type of thing. Here, the agent that's learning is taking decisions in sequence. And so we're going to go through a few examples that I think will help clarify this. So to start off, let's take a very, very simple example. So this is what we'd call a grid world, where you just have, here we have 16 grids or grid cells. These are the little squares. And this blue circle is the agent. And so the agent can be in any one of these cells, and it can move up, down, left, right, and sort of navigate in this grid world. And the goal of this agent is to get this star. So once it gets that star, it's happy, and that gives it a good reward. And so the agent needs to learn how to get to this reward. So obviously this is a very simple problem, but it's useful to help illustrate some of the challenges in reinforcement learning. So if we have the system like this, we can look at it and very easily say, well, the best thing you can do to get to that star as fast as possible is one thing you can do is go right and then go down. Obviously, there's another course of action you can take, which is go down and then go right. And you can maybe zigzag your way around, but that might take you a bit longer to get to the star. And really, you want to get there as fast as possible. So this is fine. This is what we'd call a plan. So this is a plan to get to the star. But in reinforcement learning, we typically don't know where the star is, and we often don't even know where we're going to end up when we take an action. So if the agent says take the right action, it doesn't really know what right means. So when I say right, it means something to you people because we've grown up learning these words. But really, for an agent, this would be action, say, action 2. And so action 2 really has no semantic meaning to the agent. So the agent could end up here after taking action 2, or it could end up exactly where it started. That's what the agent has to learn, the consequences of these actions, and needs to sort of figure out what's hidden behind these gray squares, so as to find the reward and try to maximize the reward it receives. So let's say the agent plays around and tries a few actions, as illustrated here, and eventually discovers this part of the grid world. So that's fine. So the agent really hasn't found any reward. Everything is basically no reward until now. So that means that the agent doesn't really have any incentive to do anything other than kind of choose actions randomly, and that's fine. But let's say after a while it does find this little star here. And so this star gives it a little bit of reward. And so the agent might say, well, I'm happy with that. I can always go right and then go down and I get this little star. And it might leave this area unexplored. That means it didn't go find what's underneath these gray squares. And it could be that there's an even bigger star over here at the bottom right. But the agent doesn't know this yet because it hasn't gone down here. So at this point, the agent may decide to just stick with what it already knows and stick with this small star, or try to explore a bit more and get this larger star. So I am going to give little glimpses into the math of reinforcement learning, just for those of you that are more mathematically inclined. Maybe this will pique your interest. But there is a lot of math in reinforcement learning, which for me is something that makes it really interesting. But we're not going to do too much math in this talk. So we typically define these problems that the agent, where a reinforcement learning agent has to interact, as a Markov decision process. And so again, I won't go too much into the math, but basically it consists of a set of states. So in this case, the set of states are the little grid cells where the agent can be in. So there's 16 states, 16 grid cells that the agent can be in. Actions, so what are the actions that the agent can take? And so in this case, they're up, down, left, right. P defines the transition dynamics. So in this case, it's a pretty simple problem where if we say right, we're going to go one cell to the right. But there can be other systems where the transitions are a bit more complicated and they're stochastic. So that means that they're probabilistic. So it could be that this floor of this grid cell is a little slippery. And it could be that if you say take the right action, 90% of the time you end up here, but it could be that 10% of the time you actually don't move. So this makes it a little more challenging because if you take three right actions, if everything is deterministic, that means that we always move to the right cell. If we take the right action, we know with 100% certainty that we're going to be in this cell. But if we have the stochastic transitions that I was mentioning, we don't know with 100% that we're going to be here. We're going to know with 90% we're going to go here. And then if we're here, then another 90% we're going to end up here. And with another 90% we're going to end up here. So that means that after taking 3 actions to the right, there's 90% cubed probability that we're actually here. And there's some other probability that we're somewhere in one of these 3 cells. The R is the reward. So basically this defines where does the agent get a reward when it's in the environment. In this case, it only gets a reward when it reaches this star here at the bottom right. And gamma, this is what's called a discount factor. I won't go too much into the math of this, but essentially what this encourages is for the agent to not wait too long before receiving the rewards. So as I said, we could take a lot of paths. We could take a really windy path that goes throughout all the grid world, then eventually reaches the star. But that's a pretty slow way to get to the star. And so this gamma is actually discouraging the agent from taking these long paths. And the agent, because of the gamma, or in part because of it, wants to get to the star or the rewards as fast as possible. Okay, so we typically define the agent's behavior, so how it chooses its actions, as a policy. And so this is a function that's basically taking for every state that it's in, it's going to tell it what action to take. So we say a distribution over actions because in general, it could say, go to the right 50% of the time or go down 50% of the time, because there's 2 paths you can take. So it might choose to do that. In the first state, it might pick one or the other by a coin flip. But in general, this policy tells the agent for each state it's in what action to take. And so some policies are good, some policies are not good. And the agent really, its ultimate goal is to find the best policy that can make it maximize the rewards in as little time as possible. And so again, this is really just to pique your interest. So we can formalize this very crisply with math, with these equations for the value functions. And so this basically just says, what's the value of each state, S, given that I'm following a particular policy pi? And what the agent is trying to find is the optimal policy, which also gives you the optimal value function. And again, I won't go too much into the math, but there's some really interesting math in here, and you can prove some nice things. So if you're into math, I encourage you to check this out. Okay, again, just a quick glimpse of some of the functions that we look at in reinforcement learning, and the behavior policies and how the optimal behavior is defined with respect to one of these functions that we're trying to find. Okay, so enough piquing your interest with the math. Let's go back to the higher level, simpler, more intuitive examples of the small grid world. So as I was saying, if you know all the grid world, so you know exactly where all the cells are, and you know what the actions do, and you know where the rewards are, then this is what's known as a planning problem. So really what we're trying to do is plan how to get from the top left to the bottom right. So this example is very, very simple, so we can do this in our head. But in general, planning does deal with very complex problems where the solution isn't as evident as it is here. So there are sophisticated algorithms to find optimal or near optimal plans. As I mentioned in reinforcement learning, we don't know all the states. We don't know where the rewards are, and we don't know how the actions affect where the agent is or how they bring rewards. So this is what the agent has to learn by interacting with the environment. So I alluded to this a little bit before. One of the key problems and key areas of research in reinforcement learning, and it has been pretty much since the beginning, is the notion of exploration. So as I mentioned, we could have this agent that found this little star over here. And so it gets a little reward, and maybe the agent is happy with that and says, you know what, I want to play it safe, and I'm just going to stick with this reward. And so it could very well decide to do that, and that's what we would call an exploitative policy. That means it's exploiting the knowledge it already has, and not trying out new things. But there's a flip side to that, which is exploration. So in exploration, the agent might decide to take an action that it doesn't think that it's optimal. So right now it has this quote-unquote optimal policy that always gets it to this little star. But maybe one time it decides to go down here. So this is not optimal because the agent actually doesn't know what's going to happen. It could be that this is a hole where the agent dies, and so it's a very bad thing. So the agent has to explicitly say, you know what, I'm going to try something new. It might be bad, but it might be good. And so that's what we call exploration. And so if the agent does explore, it might be able to eventually find this big star. and then realize that there's a better reward out here. Now, the problem is you don't want to explore too much, because if you're always exploring, then you're always going to be trying out random things, and you're never going to be able to say with certainty, I'm going to get you a certain amount of reward. So if you're always trying out random things, you can't guarantee 100% that you'll always reach this big star, even if you found it, because you're always going to be trying new things. But at the same time, you don't always just want to exploit, because then you might end up in the situation where you don't find the big star and you're just satisfied with this little star. And so this is a big problem, this balance of exploitation and exploration, and there's a lot of research that goes into this. It's still a very open problem. Even though there's quite a lot of theory behind it, a lot of these theoretical results don't always apply in practice when we're dealing with big problems. And so one of the simplest ways of doing exploration is what we call epsilon greedy, where basically at every step we pick the action according to what the agent thinks is optimal, with probability 1 minus epsilon. And so epsilon is just a very small value. And so with a very small probability, we'll pick a random action. So this allows the agent to sort of explore a little bit every once in a while, but most of the time it's just acting greedily according to what it thinks is the optimal policy. Okay, so I want to again come back to this comparison with what you traditionally hear about when you listen to machine learning talks or learn about machine learning models or problems. So typically now with deep learning, when we talk about these problems, what we're typically dealing with is a big data source. So this could be like images or a lot of text or music or something like that. And we feed this data through a deep network, and there's a desired outcome. So the desired outcome could be, classifying whether there's a dog or a cat in an image, or it could be actually generating a new image that matches the distribution from which we're generating. You may have seen a lot of these videos that go around social media where AI basically generates some really realistic images, and sometimes they're kind of artistic, sometimes they're kind of weird, but they're very nice. And so this is the standard supervised, or what we call supervised or unsupervised or semi-supervised learning, where we have a fixed data set, and we're feeding this data set through a deep network and trying to get the network to produce the outcome that we want. So we know what the outcome is beforehand. In reinforcement learning, we don't have a data set per se. It's not a fixed data set. Instead, what we have is an environment. Like I was mentioning before with this grid world, you have a system in the sense where the agent sends actions and the environment returns something. But it's not like the environment is handing the agent a fixed data set to play with. And we also don't have a desired outcome. So it's not like we have the optimal policy or the optimal value function lying around and we're just trying to approximate it. We're trying to learn that based on our own mistakes. So this makes it a very challenging problem because it's essentially a moving target. And so this introduces all sorts of complexities and challenges that, again, these are all very open problems that a lot of people are actively researching in. So what we do in reinforcement learning is we do what we call bootstrap, not to be confused with the traditional bootstrap from the statistics literature, but we're essentially trying to reuse prior knowledge to construct new targets for the agent to learn. So again, this is this moving target that I was mentioning. So in what we call online reinforcement learning, we have an agent that's constantly interacting with an environment via this policy, and it's adjusting this policy to try to pick better actions. And the environment is always returning it new states and new rewards, and this is how the agent learns. And for big problems, we typically use a deep network that's inside the agent. But the deep network, again, is not the only thing. And this is another key difference with traditional machine learning problems, where the main thing is the deep network. In reinforcement learning, it's part of the solution, but there's more components to the agent. So just to give another very simple example to sort of illustrate the complexities here, let's say we have this agent in this very simple 4-state environment, and it wants to learn how to behave. So let's say it goes down and oops, it runs into fire. So then it says, I don't want to go there, and comes back and then decides to go right, runs into fire again. And it says, I don't want to go there. So now the agent knows that there's fire right next to it. And so one thing it can do, again, this is where the exploration comes in. It can just say, you know what? I know these things, and I'm just going to set my moving target based on what I know. Eventually, this moving target will converge, and the agent will know that the best thing to do is actually to stay in place and not go anywhere. And this is because it's not exploring. So its quote-unquote data set is fixed because the data set is essentially just these fire cells that it already knows about, and the cell that's not burning it. So the agent you might say it converges. But again, the data set is not complete. We're missing a very key component. So it could be that if the agent explored a little bit, it reached a fire extinguisher to turn itself off, and a genie that gave it everything it wanted. So again, this is a different data set, and a data set where the agent can learn even better behavior than just staying in place, because it can actually get 3 wishes. So this data set, it's difficult to predict what the data set will look like for the agent, because it really depends on your algorithm and how the agent is collecting experience. Okay, so there is one thing that is gaining popularity nowadays. It's called offline deep reinforcement learning. And here you are given a data set that maybe was collected by an agent, or maybe if it's something dealing with health, it's health records that a hospital provides, and they want to try to use reinforcement learning to gain some knowledge about the data in that they have, but they can't really run experiments with people, because obviously you're dealing with real people. So you're really limited to this offline data set. And there's all sorts of different challenges that come in there. Very active, again, area of research. I'm doing quite a bit of research here, and it's very, very interesting and challenging. Okay, so I want to come back a bit to the environments. I was using these very simple grid worlds, and reinforcement learning has really been around since, I'd say, the 70s, at least, 1970s. And previously, before deep networks became a thing that we use commonly, we would run our experiments on these simpler environments. So this is kind of like a grid world with some cells that are problematic. You have this mountain car, where it's just a little car that you have to gain momentum to reach the goal. Cart pull is one of the classic environments where you're just trying to balance this pull on this cart, and the agent can move it right or left. So these are pretty simple problems, but they're still quite good at, especially when you're developing theoretical results. So during my PhD, I did a lot of theory. And so, my papers would typically look at, there would be a theorem, and then I'd evaluate the theoretical results on small environments, because these small environments allow you to really look into what the agent is doing. So it's a bit easier to get an intuition. But in 2012, this new suite of environments was introduced by my colleague Mark and some of his collaborators, where it's a set of 60 Atari 2600 games with this console. And so each game is very challenging. Each game is very different. And so the agent, what it's trying to do is to learn, or the researchers, what they were trying to do really is develop an algorithm that could play these games quite well. And so that's the idea is the agent is essentially controlling this joystick. Obviously, everything's running in simulation. We don't have a robot moving the joystick, but it's a simulated joystick that's playing this game. In this case, it's Space Invaders. So DeepMind, this is the first paper that really set them on the map and made them quite famous. And it's actually also the paper that's a pivotal paper that sort of kicked off what's now known as deep reinforcement learning. So they combined traditional reinforcement learning algorithms with these deep networks. And they published this in Nature. And basically, they were the first to really show how powerful this combination of reinforcement learning with deep networks could be. And so they were able to play these games. The agents that they trained were able to play, in the vast majority of games, they were able to play at superhuman levels. And so these are very challenging games, and they require quite a bit of skill. Some of you may or may not have played it, or at least you've played some other video games. And the fact that this autonomous agent was able to learn to play at superhuman levels was quite impressive. And so this, as I said, is one of the seminal papers in reinforcement learning. It's been cited thousands of times, and it's really, this is what kicked off this field that is booming right now. There's a lot of research happening. It's a very active and very exciting field. This is just, this is kind of old. You can see from 2016, but it's just showing the growth of papers. So when I did my PhD at around, I finished it around here. And so you can see that the number of papers is just continuously growing. And I think I couldn't find a newer chart, but this, I'm sure it's not growing as constant as it is here. It's really growing in probably almost exponential at this point. As I said, there's a lot of interest in this field. And part of the reason for that is that we have seen some even more examples, other than just playing Atari games, some more examples of using deep reinforcement learning for really large and challenging problems. So one of the more famous examples is AlphaGo, again, DeepMind. And basically, they trained an RL agent that beat the world champion at Go. So Go is an extremely challenging and complex game. It's arguably more complex than chess. And the fact that this agent was able to beat the world champion was truly remarkable. DeepMind also trained an RL agent to play StarCraft. This was called Alpha Star, and I think they won some world championship. But it was really, this is an extremely challenging game. I've played it once, I think, and I got lost. There's so many variables you have to keep track of. You're basically controlling an army, and you have to move around the map and see where your enemies are and that type of thing. Very challenging game, yet they were able to train an RL agent to play at superhuman levels. Recently, some colleagues published a paper at Nature where they use reinforcement learning for optimal chip placement. So when you're designing chips, the chips that we actually use to train these deep networks, where you place the chip actually affects the performance of these, or where you place the different components of these chips affects the performance of this hardware. And so they were able to use reinforcement learning to really hyper-optimize the performance of these things, reduce energy consumption, and that type of thing. It was truly remarkable. And it's a nice sort of feedback loop where we're using RL to design chips to train RL even faster. And myself and some colleagues, we published a paper in Nature about a year ago where we were using deep reinforcement learning to control these stratospheric balloons. So this is a balloon that flies in the stratosphere. This was a company that has since folded, but it was an Alphabet company called Loon. And they were building these balloons to deliver internet to remote areas of the world. So if it's too expensive or it's physically impossible to build a cell tower, well, you can send these balloons. And so this was a really challenging problem because they're flying up in the stratosphere. And so the way the balloon flies, it flies in a sort of passive way. So it's just drifting with the wind. So it's in a sense surfing the winds. And the only control that you can have is whether to go up or down. So the task that we were trying to address is that these balloons, because they're delivering internet to a particular area, this is what we call the station keeping range. So we want this balloon to sort of stay here to deliver internet to this area. Now, because it's surfing the winds and the winds in the stratosphere are always blowing, it's not like you can say, okay, stop, and it'll stay there. If you say stop, the winds will just push it away. And so you end up having to do these complex figure eight type maneuvers where the balloon is sort of surfing these winds and trying to stay in place. But again, there's a lot of uncertainty because you can't see all of the winds around you. So the balloon has some sensors that tell it the wind's nearby, and it has some forecasts. These forecasts may be more uncertain than others. And so it's using all of this information to fly this balloon. The other challenge is that they're solar-powered balloons. So obviously, when they're using power at night, they run the risk of running out of power. So it's very important for the controller to learn how to navigate to these areas of desire quickly and to stay there, but also to not use up too much energy. So this is just a little simulation we ran to sort of show how these balloons fly. So this red dot is the balloon. This circle here, this is the area, the station keeping range, where the balloon wants to stay inside. And over here on the right, we have what we call the wind vector. So the balloon is over here, and these are the directions of the wind, where the wind is blowing and the magnitude with which it's blowing. So blue means that it's very uncertain. So you can see the further away you are from the balloon, the more uncertain the balloon is of those winds. And when it's red, it means it's more certain about those winds. And so you can see that these winds are just constantly blowing, and the balloon really has to be clever to try to stay within the station keeping range. And it's a very challenging problem. And so these are the actions that the agent can take. It can say go down, it can say stay, or it can say go up. So you can see it's never really like you have one clear winner. There's always a little balance between all of these actions, and it's quite a challenging problem for the agent to be able to maintain within this range. So here we have the battery. This is just a bug in our simulation. It means that there's excess power at that point because the sun is shining and it has energy. But this is just to give you an idea of some of the challenges we faced with this problem. And so what we were, this is what the agent, the reinforcement learning agent, is receiving as input. So it's basically receiving this, and based on this is essentially its state to harken back to the grid worlds that we were observing. So you can see this is quite a bit more complex than the grid world. And so we're getting all sorts of features like the altitude, how much battery it has, where the sun is. The sun is very important because not just for power, but also it affects temperature. So the balloon, it's a physical thing, so it's affected by temperature. The pressure inside the balloon is affected by temperature. The radiation that comes off of the Earth also affects temperature. The clouds underneath the balloon affect how much radiation bounces off the Earth. So it's a really, really complex and challenging problem. And so we have a bunch of features like this, and then we have this wind column, the wind feature vector that I showed you, which is basically where the wind is blowing, how fast above and below the balloon, and the level of uncertainty we have. And so what we were competing against was this controller that we call the station seeker. And this controller was something that lots of PhDs, people with PhDs in these types of stratospheric balloons and wind and dynamical systems, they designed, and it worked quite well. So what we're measuring here is the time within the radius. So there's a 50-kilometer radius that we're interested in delivering internet. And so this is the metric that we're looking at. So for 2 days of flying, how much time could you spend within the radius? So you can see the controller that they had, the sophisticated controller, was about 40.5. And we were able to train our agent to go all the way up to 55.1. And so this might seem like not great because it's just over 50%. But we ran quite a few simulations to get an estimate for what is the best any agent can do. Because again, there are certain winds that are just, there's nothing you can do. If the wind is just blowing in one direction, there's really not much you can do at that point because you can't fly against the wind. And so this is really the reasonable range. You cannot get any higher than this. And so we can see that we're essentially almost in this area of optimality. This green agent is something that we devised in simulation, and this is essentially doing a tree look ahead. So it's assuming you can look into the future and do some planning there. And so you can see even with that privileged information, which you would not be able to have in the real world, we're still able to beat that. So here what we're showing is the progress of our training of these agents. So this is the station seeker, and what we're visualizing here is the power. So what we really want is to go more to the left because we want to use less power. And this is the time within that radius. So here we want a higher value because we want to be more time within that radius. And so station seeker, which is the sophisticated controller that we're using before, is about here. So it has this kind of trade-off between power consumption and time within that radius. These red dots show our agent as we were training it. So this is when we trained it for 12 hours. So you can see it's using less power. Already just within 12 hours, it's using less power than station seeker, and it's still within more time spending within the radius. But you can see the progress as we train it more and more. And after almost a month of training, we can see it's really staying well at this value of 55.1% within the radius. And we're using no more power than station seeker. So for the same amount of power, we're able to by far exceed what they had before. And with this controller that has the privileged information, you can see that even at about the same levels of power, it's not able to match our old controller. So this was extremely exciting. And we actually did fly quite a few of these balloons in the real world. So we had reinforcement learning in the air, which was very exciting. And this is a video that it's a simulation that allows us to compare the stability of these agents. So what we did is we deployed 100 balloons that were almost right on top of each other. But this shows you within simulation, even though they started very close to each other, they immediately start to spread. So just slight variations in the initial conditions end up with very different outcomes for these balloons. So we can see that our learned controller in red, they're sticking much more closely together than the station seeker, the previous controller. And so what this demonstrates is that our agent is much more reliable in the sense that it's less sensitive to these initial conditions, which we can see that the station seeker one is less able to sort of maintain the stability based on variations in the initial condition. So again, very exciting, and this is really challenging, but also a very rewarding project that we worked on. Okay, so I hope that that was enough to get you all interested in this space. Again, it's a very active space. There's lots of research happening in it. You get to generate these fun videos. A lot of it has to do with games. So if you're a gamer person, it's kind of fun to get to learn these old video games. And there's newer video games that people, like StarCraft, that people train RL agents on. There's also a whole field that I didn't even touch on. I don't do much research in that, but in robotics. So a lot of people use reinforcement learning for robotics. And this could be navigation robotics, or one of a popular robot is a hand. So it's a gripping hand. And so they're training these hands how to grasp objects and generalize. So, if it learns to grab a cup, can it then grab a ball? So this seems like an easy problem for us humans, but it's actually very challenging for reinforcement learning and with robots. So if you want a bit more of a technical introduction, you can go to my site here. I have a video and a blog post, and it has a Colab notebook, a Jupyter notebook, where you can follow along. So if you want to learn a bit more about reinforcement learning and actually start writing code to play around with it, I encourage you to check that out. If you want to go even deeper and really learn the core of reinforcement learning, this is sort of the canonical reference for reinforcement learning, written by Rich Sutton and Andy Bartow. And Rich Sutton is a prof at U of Alberta, but also with DeepMind, and Andy Bartow is an emeritus prof at UMass Amherst. Really great book. I learned reinforcement learning from this book, from the first edition, and it's an excellent book. And finally, I'm the tech lead of this library, reinforcement learning library called Dopamine. And this is really a library written for researchers. It's written in Python, but it uses this library called JAX, also TensorFlow, but the one we've been using more is JAX. It makes it very, we hope, easy to start playing around with things. And so the introduction to RL that I mentioned earlier is using Dopamine for some of the more advanced concepts. So again, encourage you to check it out and try it out. There's lots of documentation there. And with that, thank you very much. I hope that was interesting. And more importantly, I hope that piqued your interest to get into this field. And I will be around for some questions. Thank you.
Pois é, aí galera, então aqui a gente terminou a parte gravada e agora vamos ter as perguntas e respostas com o Pablo. Pablo.
Hello, hola.
Ok. Então, podem mandar as perguntas aí. Okay. The first question is from Fabio. Is it true that playing large games like Tetris and chess help in how we develop our daily logic? But does this apply even more to reinforcement learning? I think you can talk about like transfer learning.
So I guess the first part of the question is talking about us as humans, which I guess is true. I mean, any type of exercise I find helps in different ways. These being logical games, I assume they help with logic. For reinforcement learning, I'm not sure. So typically, like when you see the examples of reinforcement learning that I was showing, that playing Go and those types of things, they're typically trained. I'm sorry if there's a lot of background noise, by the way. I hope you can hear me well. You typically train those for a specific game. So you train it to play Go, or you train it to play chess, or you train it to play Tetris. And very rarely do you take an agent that was trained to play chess and try to get it to play Tetris. It won't be able to. For a number of reasons, some of them being just the rules of the game are very different. Sometimes you encode the rules of the game in the agent, sometimes you don't. But you typically have to retrain from scratch. And it's actually a very interesting area, this sort of lifelong learning, where you don't have to retrain everything from scratch. I mean, you can reuse previous knowledge that you gained from perhaps different tasks. But it's still a pretty new area. In reinforcement learning, most of the time we're just retraining from scratch. It's kind of wasteful, so I do hope we start seeing more instances where people don't have to retrain from scratch and are able to leverage prior knowledge.
Thanks for this first answer. And let's see the next one. Okay, this one is from Giuliano. I would like to... Okay. Right. Do you think it's possible to use reinforcement learning for train programming? It's a combinatorially NP hard problem.
Yeah, that's an interesting question. So there is a growing area of research in trying to use RL for combinatorics and combinatorial problems. Part of the difficulty with a lot of these combinatorial problems is that they're typically restricted to be things like integers, which are often they're not differentiable, so they become really difficult to use with deep networks. So even before we go into deep networks, so for a lot of the algorithms that we use, approximation algorithms that we use for these very hard constraint satisfaction problems that require integers and things like that, is to relax them. And so we solve them using reals, and then we sort of approximate them to the nearest integer. And these are approximation algorithms that have been around for a long time. And I think some people are now starting to do something similar with reinforcement learning, with varied success. I mean, you can sometimes show empirically that some things work. So you might be able to get something interesting with reinforcement learning. The problem is, I don't think, as far as I know, there's no like hard theory on these types of problems with reinforcement learning. So you don't necessarily have a guarantee that things will work. And when you get into deep reinforcement learning, a lot of the secret sauce is in the hyperparameters used, and this is typically problem specific, so it requires a lot of time. You can't just take an out of the box solution and plug it in. It's unlikely it'll work. You need to do some hyperparameter optimization. So I'd say it's possible, but no guarantees that it'll work, or it'll work better than some other non-RL solutions that are out there, such as the approximation algorithms I was mentioning.
Nice. Thanks for this answer. Next question. Okay. So, have you ever faced a situation in which the algorithm took a completely unexpected path? Can new problems arise in the process?
Yeah, that's an interesting question. The algorithms, their behaviors often surprise us. And I think, especially when we're dealing with things like games, right? Because most of us have been playing games for most of our lives, so we have certain expectations for how to play a game, and so we play with our peers, and our peers kind of play in relatively similar ways to us. And so when a computer comes along, it does not play like a human at all, because it didn't grow up playing with other humans. It's just optimizing a numerical function. And so, for instance, if you like Montezuma's Revenge, right? That's one of the harder games in Atari. It's a very hard game because anytime you die, you start from the beginning again. And so it's this really hard game where you have to, get keys, open doors, and then switch rooms. And you have to go through like, I don't know, like 30 different rooms. And you might be in like one of the last rooms, but if you die there, you have to start all the way back from the beginning and redo everything. And so that makes it really, really hard to do. And so for reinforcement learning agents that aren't very good and aren't able to handle these exploration problems, what ends up happening is you often just see them stay put and they don't play the game, because it's better numerically to not die than to try something and then probably die. So this is a very boring way to play the game. Like, no human is ever going to just stay put and say, I'm not doing anything because I might die. No, because you want to try to play the game. And so these types of behaviors are always kind of surprising. Another example that I think is a bit more interesting is AlphaGo. When it was playing against one of the world champions, the move it made, so you have people commenting on the moves, and these are experts in Go, and it made some move at some point, and everybody thought it was a mistake, and they said, "Oh, the algorithm made a bad move there. Like, I've never seen this. This is something went wrong. It's gonna lose." And then only like 20 steps later, the reason for that move became apparent, and the algorithm won the game. And this was just mind blowing for all the people because they had never seen a move like this. And so this basically taught them a new strategy that they didn't know about before. And again, this it's just because the algorithm is just optimizing a numerical objective. It's not following, how its friends play or anything like that. It's learning that just through self-play. So yeah, you can often be surprised. Hopefully, most of the time, it's if you've designed things well, it's for a good reason that you're surprised, and it's not something bad that's happened.
Yeah, there's even a book, I think it's called Game Changer, by two chess international masters that they analyze AlphaZero's games and what new motifs and strategies for chess arise. So, yeah, it's pretty cool. Next question. Okay. In chess, agents are ahead of humans, but their kind of play is still very distinguishable from top-level humans. What is the current research progress on making these agents act more human-like?
Yeah, so this is related to, I guess, the previous question. I don't know if there is any research trying to make these agents more human-like. Maybe I would be very surprised if for chess they're trying to do that, because so the whole point of doing this type of research, of training these agents to play chess, is not to have a computer that plays better than humans just because we want that, or we want a friend to play chess with. The reason is that we're trying to advance the state of the art of reinforcement learning research, and we're trying to make these show the capabilities of these algorithms. So why did part of the pivotal moment for deep reinforcement learning was when DeepMind published that paper where they showed they could train agents to play Atari games at superhuman levels. And so why were they doing that? They didn't want to do that because they wanted an agent to play Atari games. Like, that's not really that practical, especially not at that point. These are Atari games from the 1980s. The reason for that is that because prior to that, no other computer could do that. So when they did that, that basically demonstrated that what was possible with computers. And so it's really sort of pushing the limits of what you can do with these algorithms and these computers. And so now that we've sort of passed that hurdle in chess, and that we can train these agents that are superhuman, my suspicion is nobody's really looking at that problem that much, other than to design perhaps more sample efficient methods or something like that, or to get new strategies for chess. But now most researchers that are in this type of groundbreaking challenges, they're probably looking at harder problems where we don't yet have superhuman performance.
Thanks for the answer. Another question is, what made you want to pursue this area of research?
So in my undergrad, my last semester of my undergrad, I took, or my last year of undergrad, I took the first artificial intelligence course offered at McGill, which is where I was studying. And it sounded neat. I mean, you'd heard about artificial intelligence, so I took that. And the prof that was giving that course was doing a pre-cup, and it was her first. She had just joined McGill, so it was her first time teaching that course. And I really liked the course. I thought it was super interesting, and I did my honors project with her. So here I was building neural nets, but by hand, in a sense. So I was in C++ writing up all the neurons. We didn't have TensorFlow or JAX or anything like that. So you really had to write everything and take the derivatives by hand and sort of write yourself the code to backpropagate everything. And it was fun, great experience. It didn't work at all, the neural network. I mean, it worked, but it didn't learn anything. But that's beyond the point. It was interesting to do that. So that got me really interested in that space. And but after my undergrad, I worked for a few years, not in AI or anything like that. And then I went back to grad school. And when I went back to grad school, one of the big reasons why I did go back is because I ran into doing a pre-cup who taught that course on the street, and she suggested I go back to do a master's. And I was kind of looking for something new, so I decided to go back and do it with her. And her area of specialty is reinforcement learning, so that's what got me into it. And I really liked it as soon as I learned about it.
And I guess for our final question is, what are the opportunities in the industry or academia for working with reinforcement learning?
Sorry, it got a little choppy. I think, if I understood correctly, the question is, what are the opportunities in industry and academia for working with reinforcement learning? So there's lots right now, much more than what there used to be 10 years ago. So I finished my PhD 10 years ago, and I had a really hard time finding a job, to the point where I left academia. So I joined Google to be a software engineer because I couldn't get a job in academia, which is where I wanted to be. But here I am now. I luckily was able to rejoin later. So right now there's a lot of opportunities. It's still mostly an academic profession, reinforcement learning. It's people doing fundamental research, but you're starting to see more industry, more positions using reinforcement learning for applied problems. So at Google we have a couple projects that use reinforcement learning. I mean, we used it with a company called Loom to fly stratospheric balloons. They're using it in YouTube recommendations. I know the Bank of Canada was using reinforcement learning, and they launched some product with using it. Salesforce, I think, is also using it. Sorry, not Bank of Canada, Royal Bank of Canada, which is the non-public entity. So you're starting to see more applied reinforcement learning coming out. Difficult space, it's a difficult problem, and so the fact that you don't hear that much about them it's not necessarily that people aren't working on it. It's just a hard problem, and so you might not hear of it for a while until they get it working correctly. Because for a lot of these applications, depending if it's there's issues with safety or anything like that, you want to be really sure that it behaves somewhat in an expected way so that you can avoid any catastrophes.
Okay, so thanks a lot for that answer. And yeah, I think that's it. Vamos agora passar uma coisa dos nossos patrocinadores. And thank you very much, Pablo, for giving this amazing talk.
Thank you for inviting me, and I hope the background noise wasn't too bad.
No problem.
All right. Have a good week, everyone.
Bye. Ah, não tem nada outros patrocinadores, né? Então, acho que é isso, gente. Valeu. Até mais.